As you listen to this, Saturn floats 800 million miles from where you are sitting. If you left Earth today, traveling at the speed of a bullet, you would not arrive for over 50 years. Every spacecraft humanity has ever sent to the ringed giant required between 3 and 7 years just to get there. And Saturn is not even far by cosmic standards. It sits in our own solar system, orbiting the same star that warms your face on summer afternoons. This is our neighborhood. This is close. The distances separating us from this neighboring world are so vast that they break every intuition your brain evolved to process. The true journey time to Saturn depends entirely on how fast you are willing to go. And most speeds we consider fast will leave your bones as dust long before arrival. If you want to understand just how isolated we are within our own cosmic neighborhood, please like and subscribe. It truly helps our channel grow. This journey through the void will reveal truths about existence that will change how you see everything. Are you ready? Let's begin. Saturn does not sit at a fixed distance from Earth. This fundamental fact creates the first obstacle in calculating any journey, a time to the ringed planet. Both worlds orbit the Sun at different speeds along different orbital paths, creating a cosmic dance where the gap between them constantly shifts across hundreds of millions of miles throughout each Earth year. When Earth and Saturn align on the same side of the Sun during what astronomers call opposition, the distance between them shrinks to approximately 746 million miles. This represents our closest approach, the optimal launch window that mission planners wait years to exploit. Space agencies build their entire program schedules around these alignment windows because launching during unfavorable orbital configurations can add years to journey times or require fuel quantities that exceed any practical rocket's capacity. But when both planets occupy opposite sides of their orbits with the Sun burning between them, that distance stretches to nearly 1 billion miles. The difference between closest approach and maximum separation spans approximately 250 million miles. This variance alone exceeds the distance from Earth to the Sun itself. The gap that separates you from Saturn tonight differs from the gap that will separate you from Saturn 18 months from now by a distance larger than the entire inner solar system. The average distance to Saturn measures approximately 886 million miles. Scientists express this as roughly 9.5 astronomical units, where 1 astronomical unit equals the average distance from Earth to the Sun, about 93 million miles. This measurement system exists precisely because raw mile counts become meaningless when dealing with interplanetary scales. The human brain did not evolve to process numbers with 9 digits. We lack intuitive frameworks for distances that require hours for light to cross. Launch windows to Saturn open approximately every 12.5 months as Earth catches up to and passes the slower-moving ringed planet in its orbit. Missing an optimal window does not simply delay a mission by days or weeks. It can add years to journey times or require redesigning entire trajectories. The Cassini mission, for example, was carefully planned around a specific planetary alignment that allowed gravity assists from Venus, Earth, and Jupiter. Had that launch window been missed, engineers would have needed to calculate entirely new routes through the solar system, potentially adding years to an already lengthy journey. This orbital choreography means that patience becomes a mission requirement before any spacecraft leaves the ground. Teams sometimes wait years for favorable alignments, knowing that rushing to launch during suboptimal windows would waste fuel, extend journey times, or both. The planets move according to gravitational laws that human schedules cannot influence. Saturn arrives at opposition when orbital mechanics dictate, not when program managers prefer. Consider what 886 million miles actually means in terms your brain can process. Light itself, traveling at 186,000 miles per second, the fastest speed possible in our universe, requires over an hour to cross this gulf. When mission controllers at the Jet Propulsion Laboratory send commands to spacecraft orbiting Saturn, They transmit their instructions and then wait, sometimes over 80 minutes, depending on planetary positions, just to learn whether the signal was received. To put this distance in more tangible terms, consider driving around Earth's equator. The circumference of our planet at the equator measures roughly 25,000 miles. Driving this distance at highway speeds would require approximately 17 days of continuous travel. Now, imagine completing that equatorial circuit not once, but 35,000 times. That is the distance to Saturn. 35,000 trips around the entire planet Earth, back to back, without stopping. Or consider the distance in terms of the Moon, humanity's only extraterrestrial destination for crewed missions. The Apollo astronauts travelled approximately 240,000 miles to reach the lunar surface, a journey requiring 3 days. Saturn lies roughly 3,700 times farther away. If reaching the Moon is like walking to your mailbox, reaching Saturn is like walking from New York to Los Angeles and back again, 17 times over. This communication delay creates operational challenges that compound across years of mission duration. Engineers cannot pilot spacecraft at Saturn in real time. Every maneuver must be planned hours in advance, programmed into onboard computers with contingencies for every possible failure mode, and then executed autonomously, while ground teams wait helplessly for confirmation signals traveling at the cosmic speed limit. If something goes wrong, the spacecraft must solve its own problems using pre-programmed responses because any help from Earth arrives too late to matter. Imagine driving a car where every turn of the steering wheel takes effect 70 minutes after you move it. Imagine navigating rush hour traffic with 90-minute reaction delays. This is the reality of operating spacecraft at Saturn. The probe you are controlling right now is responding to commands you sent before lunch. The data you are receiving right now describes a situation that existed before your afternoon coffee break. The spacecraft operates in a perpetual past tense, forever separated from real-time human guidance by the cruel mathematics of distance divided by the speed of light. But light speed remains forever beyond human reach with current physics. Every spacecraft we have ever built travels at tiny fractions of this cosmic speed limit. The Voyager 1 probe, launched in 1977 and currently sailing through interstellar space, moves at approximately 38,000 miles per hour relative to the Sun. This velocity sounds impressive because it is impressive by every earthly standard. Commercial aircraft cruise at roughly 550 miles per hour. The fastest bullet travels at perhaps 2,500 miles per hour. 38,000 miles per hour represents speed that would circumnavigate Earth in just 40 minutes. Until you realize that light speed equals 670 million miles per hour, Voyager 1, the fastest object humanity has ever sent into deep space, travels at roughly 1/18,000th the speed of light. If light were a commercial airliner traveling from New York to Los Angeles, Voyager 1 would be a snail crossing the same runway, making progress measurable only with patience measured in years. To visualize the scale separating Earth from Saturn, imagine shrinking the Sun to the size of a basketball. At this scale, the proportions of the solar system remain accurate, while the distances become comprehensible. Earth becomes a tiny peppercorn, smaller than a green pea, orbiting 26 yards away from the basketball Sun. You could stand at the Sun and see Earth as a barely visible speck at the distance of a first down marker on a football field. Saturn becomes a marble, perhaps the size of a large shooter, circling 240 yards from the basketball Sun. That distance of 240 yards represents 9.5 astronomical units scaled to human dimensions. 240 yards spans nearly 2.5 football fields laid end to end. At this scale, the entire inner solar system from Mercury to Mars fits within 50 yards of the basketball Sun. Saturn floats alone in the cosmic suburbs, separated from its inner neighbours by an abyss that looks even more intimidating when shrunk to comprehensible proportions. Now consider crossing that 240 yards. Walking at a leisurely pace, You could cover the distance in perhaps 2 minutes. A brisk jog would get you there in under a minute. The journey seems trivial when compressed to backyard dimensions, but you are not walking across a grassy field on a pleasant afternoon. You are travelling through a vacuum where no fuel stations exist, where no rescue services operate, where one mistake in navigation or propulsion means death in the cold darkness between worlds. Every pound of payload you carry requires thousands of pounds of fuel to accelerate and decelerate across the void. The scale becomes even more disturbing when you examine just how empty interplanetary space actually is. Between Earth and Saturn lies essentially nothing. The void is not metaphorical. It is literal. A few asteroids drift through the main belt between Mars and Jupiter, rocky remnants from the solar system's formation that never coalesced into a planet because Jupiter's gravity stirred them into chaos. Microscopic dust particles float through the solar wind, remnants of cometary tails and asteroid collisions. Occasional comets pass on their elliptical journeys around the Sun, dirty snowballs left over from the solar system's earliest days. But for practical purposes, the gulf separating Earth from Saturn contains vacuum so perfect that laboratories on Earth cannot replicate it. The best vacuum chambers human technology can produce contain roughly 1 million molecules per cubic centimetre. Interplanetary space contains perhaps 5 molecules per cubic centimetre near Earth's orbit, dropping to nearly zero in the outer reaches. You could fit the entire atmosphere of the space between planets into a volume smaller than a single breath. If you could somehow stand in that void between worlds, the experience would be unlike anything possible on Earth. No sound would reach your ears because sound requires air molecules to transmit vibrations. No wind would touch your skin because wind requires atmosphere. The temperature would be defined not by air but by radiation, with surfaces facing the sun heating while surfaces in shadow cooled toward absolute zero. You would float in perfect silence, surrounded by stars that never twinkle because twinkling requires atmosphere to distort starlight. The nearest object might be millions of miles away, farther than you could travel in a lifetime with any propulsion system currently available. The loneliness would be absolute, not the loneliness of an empty room or a deserted island, but the loneliness of being the only organized matter for distances that dwarf continental scales. This is the void that spacecraft must cross to reach Saturn, millions upon millions of miles of nothing punctuated by occasional rocks, too small to see until you are about to collide with them. This emptiness means that spacecraft cannot refuel during their journeys. There are no cosmic gas stations floating in the void, no supply depots awaiting travelers at convenient waypoints. Every drop of propellant needed for the entire mission, every course correction, every orbital insertion burn, every contingency maneuver for emergencies that might occur 7 years into the journey must be calculated and provisioned before leaving Earth. The fuel tank sealed at launch remains the only fuel tank for the entire mission. The fuel requirements for reaching Saturn exceed what most people imagine by orders of magnitude. A common misconception pictures spacecraft coasting effortlessly through frictionless space, requiring only a brief push at the beginning and another brief push at the end. The reality involves exponential mathematics that would make most taxpayers question whether space exploration is worth the expense. Chemical rockets, the only proven technology for launching payloads to interplanetary destinations, face fundamental efficiency limits imposed by physics itself. The exhaust velocity of burning hydrogen and oxygen, our most efficient chemical propellant combination developed over decades of research and engineering. This limit is not an engineering shortcoming awaiting a clever solution. It emerges from the chemistry of combustion itself. You cannot extract more energy from hydrogen and oxygen reacting than their molecular bonds contain. This exhaust velocity limit determines how much speed a rocket can gain from a given amount of fuel through a relationship that Konstantin Tsiolkovsky described in 1897, decades before the first rockets flew. The Tsiolkovsky equation, sometimes called the rocket equation, reveals a cruel truth about space travel. The relationship between fuel mass and velocity change is logarithmic, meaning that gaining more speed requires exponentially more fuel. The tyranny of the rocket equation, as engineers call it without irony, creates exponential fuel requirements for any increase in mission capability. Want to carry twice as much payload to Saturn? You need far more than twice as much fuel because that extra fuel itself has mass that requires fuel to accelerate. The extra fuel for the extra fuel requires more fuel still. The mathematics spirals upward in a vicious cycle until practical limits make ambitious missions impossible with chemical propulsion alone. Consider a simple example. If your rocket has an exhaust velocity of 4 km per second and you want to change your velocity by 4 km per second, you need to carry fuel equal to roughly 1.7 times your payload mass. But if you want to change velocity by 8 km per second, you do not need 3.4 times your payload mass. You need approximately 6.4 times your payload mass. Double the velocity change requires nearly quadrupling the fuel. This exponential relationship crushes dreams of rapid interplanetary travel using chemical rockets. Mission planners discovered a way around this limitation decades ago through gravity assists, sometimes called gravitational slingshots. By flying spacecraft close to other planets along carefully calculated trajectories, they can steal orbital momentum from those worlds, gaining speed without burning a single drop of fuel. The planet loses an infinitesimal fraction of its orbital energy, while the spacecraft gains significant velocity. It is cosmic pickpocketing on a planetary scale. Jupiter has donated more speed to human spacecraft than any other body in the solar system. The giant planet's enormous gravity, and rapid orbital velocity make it the perfect target for gravity assists. Spacecraft falling toward Jupiter and then swinging around it can gain tens of thousands of miles per hour in velocity, the equivalent of burning tons of fuel that the spacecraft never had to carry. But gravity assists require patience. The optimal trajectory to Saturn rarely points directly at the destination. Instead, spacecraft loop through the inner solar system on complex paths that look insane to anyone expecting direct routes. They swing past Venus once or twice, using the second planet's gravity to redirect their orbits. They return to Earth for another gravitational boost, essentially bouncing off their home planet to gain speed. Some missions dive toward the Sun, using our star's gravity to accelerate before climbing back out toward the outer planets. These indirect paths add years to mission durations while dramatically reducing fuel requirements. The choice between a fast, fuel-intensive direct trajectory and a slow, fuel-efficient gravity assist trajectory is not really a choice at all for most missions. The direct trajectory requires fuel quantities that exceed what any practical rocket can carry. The gravity assist trajectory merely requires time. The Cassini spacecraft, which provided humanity with its most detailed study of Saturn and its moons, followed exactly such a convoluted trajectory. Launched in 1997 from Cape Canaveral aboard a Titan 4B rocket, Cassini did not point its nose towards Saturn and fire its engines. Instead, it flew past Venus twice, in April 1998 and June 1999, stealing momentum from the cloud-shrouded world on each pass. It returned to Earth in August 1999, swinging past its home planet at an altitude of just 700 miles, close enough that mission controllers held their breath as the spacecraft screamed through the zone where satellites orbit. Then Cassini headed for Jupiter, reaching the giant planet in December 2000 and using its massive gravity well for one final acceleration. Only after this 4-year tour of the inner solar system did Cassini finally begin its journey to Saturn, arriving at the ringed planet on July 1st, 2004. The total journey required 6 years and 9 months. 7 years of patient waiting while a spacecraft the size of a school bus crawled across the solar system at speeds that would seem magical to anyone who has never contemplated interplanetary distances. 7 years represents the longest continuous journey humans have undertaken through space for a dedicated planetary mission. The Apollo astronauts who walked on the Moon, traveled for roughly 8 days round trip. The International Space Station orbits just 250 miles overhead, close enough that astronauts can see city lights and weather patterns on the surface below. Reaching Saturn requires commitment measured in presidential terms. Children entering first grade when Cassini launched were in middle school when it arrived. The psychological challenges of a 7-year journey remain largely unexplored because no humans have attempted it. Every interplanetary mission to date has been robotic. Machines do not suffer from isolation, boredom, or the creeping psychological deterioration that extended confinement produces in social primates evolved for the open savannas of Africa. Robots do not miss their families. They do not grow depressed staring at the same 4 walls. They do not develop interpersonal conflicts with crewmates they cannot escape. Humans would face all of these challenges and more on a journey to Saturn. The current record for continuous human spaceflight belongs to Valery Polyakov, who spent 437 days aboard the Mir space station. This marathon mission pushed the boundaries of human psychological endurance, and it occurred in low Earth orbit, where rescue was possible and communication with family was instantaneous. A Saturn journey would last roughly 5 times longer under conditions of profound isolation that Polyakov never experienced. Yet the physics of the journey cannot be negotiated. The distance exists whether humans travel it or not. 886 million miles of void separate Earth from Saturn, on average, and crossing that void requires either enormous patience with current technology or propulsion systems that do not yet exist at practical scales. The energy requirements for reaching Saturn boggle comprehension when examined in detail. Escaping Earth's gravity well alone requires reaching speeds of approximately 25,000 miles per hour. Any slower, and you fall back. This escape velocity is non-negotiable, set by the mass of our planet and the universal gravitational constant. Every mission to anywhere beyond Earth orbit must first pay this entry fee, but escaping Earth represents only the first step. The spacecraft must then accelerate to interplanetary velocities that will carry it outward through the solar system. It must coast through the void for years, making minor course corrections to ensure it arrives at the right place at the right time. And finally, it must decelerate enough to enter orbit around Saturn rather than flying past the planet and continuing into the outer darkness never to return. Each of these phases demands energy. Each demand compounds the fuel requirements. Each additional pound of spacecraft mass multiplies the launch weight by factors that make program managers calculate costs in billions. The Cassini spacecraft weighed approximately 12,500 pounds at launch, including its Huygens probe, destined for Titan. This sounds substantial until you consider what was required to throw that mass towards Saturn. Launching Cassini required a Titan 4B rocket, one of the most powerful vehicles ever built, standing nearly 200 feet tall and producing over 1.7 million pounds of thrust at liftoff. The launch vehicle weighed approximately 2 million pounds at ignition. Do the mathematics and a disturbing ratio emerges. The rocket weighed more than 150 times the mass of the spacecraft it carried. For every pound that reached Saturn orbit, more than 100 pounds of rocket left the launch pad. This ratio represents the brutal economics of interplanetary travel, a toll extracted by the rocket equation from every mission attempting to cross the void. And that calculation assumes optimal trajectories with gravity assists. A direct flight without planetary flybys would require even more staggering proportions. Fuel quantities so enormous that no rocket humanity has ever built could carry them. Understanding these fundamental constraints shapes any realistic discussion of journey times to Saturn. The distance is fixed by orbital mechanics, written in the geometry of ellipses that Johannes Kepler discovered 4 centuries ago. The energy requirements are fixed by physics, encoded in equations that Isaac Newton derived from first principles. The only variables we can control are the efficiency of our propulsion systems and our willingness to wait years for the journey to complete. Current technology places Saturn firmly within reach. Humanity has already sent 4 spacecraft to the ringed planet. Pioneer 11 arrived in September 1979 after a journey of 6.5 years. Voyager 1 arrived in November 1980 after 3 years and 2 months. Voyager 2 arrived in August 1981 after 4 years. Cassini arrived in July 2004 after 6 years and 9 months. Each of these missions required between 3 and 7 years to complete the crossing, depending on trajectory choices and mission priorities. But current technology also places firm limits on how fast we can make that journey. Chemical rockets have reached their theoretical maximum efficiency. No amount of engineering cleverness can extract more exhaust velocity from burning hydrogen and oxygen than those molecules contain. Gravity assists can only provide so much free velocity, limited by the orbital speeds and gravitational fields of the planets we swing past. Without revolutionary advances in propulsion, humanity will continue measuring Saturn journeys in years rather than months or weeks. The gap between Earth and Saturn represents more than just distance. It represents the boundary between the familiar and the frontier. Mars sits close enough that round-trip communication takes only about 40 minutes at maximum separation. Rovers on Mars can receive instructions, execute them, and report results within a human attention span. Saturn sits so far that light itself requires an hour and a half for the round trip. Instructions sent at breakfast, receive responses after lunch. This communication delay fundamentally changes the nature of exploration. Robots at Saturn must be more autonomous than robots at Mars. They cannot wait for human guidance when unexpected situations arise. They must contain software sophisticated enough to recognize problems, evaluate options, and implement solutions without asking permission. The spacecraft becomes less a remote-controlled vehicle and more an independent agent operating under general guidance from distant masters. Future human missions would face isolation without precedent in human experience. For over an hour at a time, astronauts at Saturn would be completely alone in the most profound sense possible. Their calls for help would echo into the void, traveling at light speed toward Earth while the emergency that prompted them continued unfolding. Any response from mission control would arrive long after the crisis had resolved itself one way or another. The psychological distance to Saturn may ultimately prove more challenging than the physical distance. Humans evolved in small groups, where help was never more than a shout away. Our ancestors survived because they could call for assistance and receive it within seconds. We built civilizations with communication networks that now circle the globe in milliseconds. A message sent from New York reaches Tokyo before you finish speaking it. Placing humans in an environment where help is always more than an hour away, where every emergency must be solved using only the resources and people aboard, where no cavalry can ride to the rescue regardless of how desperate the situation becomes, represents a fundamental break from every experience that shaped our species over millions of years of evolution. 886 million miles. The number sits on the page, abstract and seemingly meaningless, a string of digits that the brain processes without comprehension. But behind that number lies a journey that would consume the better part of a decade from your life, that would require technologies pushing against the fundamental limits of physics, that would place travelers farther from home than any human being has ever ventured. Saturn waits in the outer darkness, close enough to see its rings through backyard telescopes on clear nights, bright enough that ancient astronomers tracked its slow wandering across the zodiac, yet separated from the world where you sit reading these words by a void so vast that crossing it remains one of humanity's greatest technical achievements. The ringed planet hangs in the sky as both an invitation and a challenge. We have sent our robotic emissaries across the gulf, but the journey times they required remind us that the solar system, despite being our cosmic backyard, operates on scales that dwarf human intuition and humble human ambition. On April 6, 1973, a spacecraft called Pioneer 11 launched from Cape Canaveral aboard an Atlas Centaur rocket. The vehicle stood 131 feet tall, its tanks filled with kerosene and liquid oxygen that would burn in a controlled explosion lasting barely 4 minutes. At the top of this pillar of fire sat a small probe, weighing just 570 pounds, bristling with instruments and carrying a gold anodized plaque depicting two human figures and Earth's location in the galaxy. Pioneer 11's primary mission targeted Jupiter, the solar system's largest planet. Engineers wanted to test whether spacecraft could survive passage through Jupiter's intense radiation belts, a gauntlet of charged particles trapped by the giant planet's magnetic field. If Pioneer 11 emerged functional from this electromagnetic storm, mission planners had grander ambitions waiting. They would use Jupiter's gravity to fling the spacecraft onward towards Saturn, making it the first human-made object to visit the ringed world. The journey to Jupiter alone required 21 months. Pioneer 11 reached the giant planet in December 1974, passing within 27,000 miles of the swirling cloud tops. At closest approach, radiation levels exceeded expectations. The spacecraft's electronics flickered. Sensors recorded particle counts that would have delivered a lethal dose to any human passenger within minutes. But Pioneer 11 survived, its systems recovering as it swung around Jupiter and emerged on the far side, accelerating at velocities no chemical rocket could have achieved from Earth alone. The giant planet's gravity bent the spacecraft's trajectory like a cosmic slingshot and accelerated it to speeds exceeding 100,000 miles per hour. This gravitational assist added roughly 20,000 miles per hour to Pioneer 11's velocity without burning a single ounce of fuel. Jupiter donated a tiny fraction of its orbital momentum. So small, the planet's orbit changed by less than the width of an atom, while Pioneer 11 gained speed that would have required thousands of pounds of additional propellant to achieve through engine burns alone. This maneuver sent Pioneer 11 racing toward an encounter that would not occur for another 5 years. 5 years of coasting through the emptiness between Jupiter and Saturn. 5 years of tracking a spacecraft that grew fainter in radio telescopes as it receded from Earth. 5 years of waiting to learn whether the gamble would pay off. On September 1, 1979, Pioneer 11 became the first spacecraft to fly past Saturn. It passed within 13,000 miles of the cloud tops, close enough to resolve individual storm systems in the amber atmosphere, close enough to feel the gravitational tug of the planet pulling at its trajectory. The spacecraft sent back the first close-up images of the rings, revealing structure invisible from Earth. What had appeared as solid bands through telescopes resolved into countless individual ringlets, gaps, and variations that hinted at complex dynamics astronomers had never suspected. Pioneer 11 discovered a new moon orbiting Saturn, later named Epimetheus, and provided the first direct measurements of Saturn's magnetic field. The data transformed theoretical models of the planet's interior, revealing a world with a dense core surrounded by metallic hydrogen compressed to states that exist nowhere on Earth. The journey from launch to Saturn encounter had taken 6.5 years. 6.5 years of continuous operation for a spacecraft built with 1970s technology. 6.5 years of nursing aging electronics, tracking a signal that grew weaker with distance, hoping that nothing critical would fail before the destination was reached. But Pioneer 11's Saturn encounter was merely a flyby. The spacecraft screamed past at over 60,000 miles per hour, gathering data for only a few hours before continuing its trajectory into the outer solar system. There was no orbit insertion, no extended study, no return to examine features missed during the brief passage. The technology of the era simply could not slow a spacecraft enough to capture it into Saturn orbit. The fuel quantities required for such a maneuver exceeded what any practical rocket of that era could carry from Earth's surface. Pioneer 11 continued outward, sending ever fainter signals until contact was lost in 1995, when its power supply could no longer sustain its transmitter. The spacecraft still exists, a silent artifact tumbling through interstellar space, carrying its golden plaque towards stars it will not approach for millions of years. Its Saturn encounter lasted hours. The journey consumed most of a decade. This ratio between travel time and science time would haunt planetary exploration for generations. The Voyager missions followed within years, carrying far more sophisticated instruments and benefiting from lessons learned during the Pioneer program. Voyager 2 launched on August 20, 1977. The naming convention seems reversed because Voyager 1 followed a faster trajectory that would cause it to arrive at both Jupiter and Saturn before its twin, despite launching later. This trajectory difference was deliberate. Mission planners faced a choice that would determine the fate of both spacecraft. A rare planetary alignment occurring once every 175 years placed Jupiter, Saturn, Uranus, and Neptune in positions that allowed a single spacecraft to visit all 4 giant planets using gravity assists. This grand tour opportunity would not recur until the 22nd century, but exploiting this alignment required sacrificing close encounters with certain moons. Voyager 1 received the assignment to examine Saturn's mysterious moon Titan, which meant flying a trajectory that would bend sharply northward after the Saturn encounter, sending the spacecraft out of the solar system's plane where no more planets awaited. Voyager 2 would follow a different path, keeping options open for continuing to Uranus and Neptune, even if this meant less detailed observations at Saturn. Voyager 1 reached Saturn on November 12, 1980, just over 3 years after launch. This journey time represented a dramatic improvement over Pioneer 11's 6.5-year odyssey. The faster trip resulted from a trajectory optimized specifically for speed, using a powerful gravity assist at Jupiter that accelerated the spacecraft along a more direct route. Mission planners accepted higher fuel consumption for the reward of reaching Saturn, while both spacecraft and ground systems remained in peak condition. The Voyager 1 encounter transformed human understanding of the Saturnian system more fundamentally than any observation before or since, except Cassini's extended mission decades later. The spacecraft discovered 3 new moons, bringing the known total to 15. It observed the complex structure of the rings in unprecedented detail, revealing thousands of individual ringlets where ground-based telescopes had shown only a few broad divisions. The famous Cassini division, that dark gap visible through amateur telescopes, turned out to contain hundreds of thin rings that appeared empty only because they were too narrow to resolve from Earth. Most significantly, Voyager 1 made the first close examination of Titan's atmosphere. This orange moon, larger than Mercury, had tantalized astronomers for decades with its thick haze that obscured the surface completely. Spectrographic observations suggested the presence of complex organic molecules, the building blocks of life, floating in an atmosphere whose composition remained unknown. Voyager 1's instruments revealed Titan's secrets in stunning detail. The moon's surface pressure exceeds Earth's by roughly 50%, meaning a human standing on Titan's surface would feel pressure equivalent to being 16 feet underwater on Earth. The atmosphere consists primarily of nitrogen, just like Earth's, but mixed with methane and complex hydrocarbons that would be toxic to terrestrial life. Organic compounds rain from the orange sky, accumulating on a surface too cold for liquid water, but potentially hospitable to chemistry, unlike anything evolved on Earth. But the focus on Titan came with a steep price. To pass close enough to the moon for detailed observations, Voyager 1's trajectory bent sharply northward after the encounter. The spacecraft rose above the plane of the solar system where the planets orbit, heading toward interstellar space on a path that would never approach another world. Voyager 1 sacrificed potential visits to Uranus and Neptune for that single close look at Saturn's most intriguing moon. The trade was considered worthwhile because Voyager 2 could still complete the grand tour if it survived to Saturn. Voyager 2 arrived at Saturn on August 25, 1981, completing a journey of 4 years from Earth. The spacecraft followed a trajectory that kept options open for continuing outward, which meant passing Saturn at greater distances than Voyager 1 had achieved. The images were slightly less detailed, the measurements slightly less precise, but the grand tour remained possible. Voyager 2 would indeed continue to Uranus in 1986 and Neptune in 1989, becoming the only spacecraft ever to visit all 4 giant planets. Both Voyager probes continue operating today, more than 47 years after launch, their nuclear power sources slowly decaying but still providing enough electricity to transmit whispered signals across billions of miles. They have crossed into interstellar space, the first human-made objects to leave the Sun's sphere of influence, still sending data about the environment beyond our solar system. The Voyager probes represented the fastest journeys to Saturn that humanity had yet achieved. Voyager 1's 3 years and 2 months from launch to arrival seemed almost magical compared to Pioneer 11's 6.5-year odyssey. But even this speed required every trick in the mission planner's toolkit. Both spacecraft launched during a rare alignment that allowed particularly efficient gravity assists from Jupiter. Both used trajectories specifically optimized for the outer solar system. Neither could have achieved such speeds through engine burns alone. For over 2 decades after the Voyager encounters, no spacecraft visited Saturn. The technological challenges of sending an orbiter seemed insurmountable with the budgets available during the 1980s and early 1990s. Flybys gathered data for hours as spacecraft screamed past their targets. An orbiter could gather data for years, following up on discoveries, returning to features that initial observations revealed as interesting, waiting for seasonal changes that occurred over decades. But getting an orbiter to Saturn required capabilities that pushed the boundaries of what space agencies could afford. The spacecraft would need enough fuel to slow down at Saturn, requiring either a massive vehicle or revolutionary propulsion. It would need to survive a journey lasting most of a decade without any possibility of repairs. It would need instruments sophisticated enough to justify the investment, and it would need political support spanning multiple administrations in multiple countries, since no single nation could afford such an ambitious project alone. Then came Cassini. The Cassini-Huygens mission represented the most ambitious planetary exploration project ever attempted when it was approved in 1989. The spacecraft consisted of 2 major components. The Cassini orbiter, built primarily by NASA with contributions from the European Space Agency and the Italian Space Agency, would spend years studying Saturn from orbit. The Huygens probe, built by the European Space Agency, would descend through Titan's atmosphere and land on the surface, returning the first images from beneath those orange clouds. Planning a mission of this complexity required international cooperation on an unprecedented scale. Engineers in Pasadena designed the orbiter. Engineers in Europe designed the probe. Engineers in Italy built the communication system that would relay Huygens data through Cassini to Earth. Thousands of scientists across dozens of countries contributed instruments, analyzed data, and argued about priorities during planning meetings that consumed entire careers. Cassini launched on October 15, 1997, aboard a Titan 4B rocket, one of the most powerful launch vehicles ever built by the United States. The spacecraft weighed 12,593 pounds at launch, making it one of the heaviest interplanetary probes ever flown. It carried 12 scientific instruments on the orbiter and 6 more on the Huygens probe, a payload that would return more data about Saturn than all previous missions combined. The trajectory that would carry Cassini to Saturn demonstrated both the power and patience required for outer solar system exploration. The spacecraft did not fly directly toward its destination. The fuel required for such a journey would have exceeded any practical rocket's capacity. Instead, Cassini performed 4 gravity assists over the course of nearly 7 years, stealing momentum from planets to gain the velocity that engines alone could never provide. The first gravity assist came at Venus on April 26, 1998, less than 7 months after launch. Cassini swung past the cloud-shrouded world at an altitude of just 176 miles, close enough that atmospheric drag became a concern. The encounter added roughly 16,000 miles per hour to the spacecraft's velocity, while redirecting its orbit back toward the inner solar system. The second Venus flyby occurred on June 24, 1999, adding more speed and setting up an encounter with Earth itself 2 months later. On August 18, 1999, Cassini passed within 725 miles of its home planet, using Earth's gravity for another velocity boost. Some observers watched nervously, as a spacecraft carrying 72 pounds of radioactive plutonium dioxide fuel flew closer to Earth than many communications satellites orbit. The final gravity assist came at Jupiter on December 30, 2000, adding roughly 10,000 miles per hour to Cassini's velocity and sending it on the final leg of its journey to Saturn. This Jupiter encounter also served as a shakedown for the spacecraft's instruments, returning detailed images of the giant planet that complemented and extended Voyager observations from 2 decades earlier. On July 1, 2004, after 6 years and 9 months of travel, Cassini finally reached its destination. The spacecraft fired its main engine for 96 minutes, the longest engine burn in its history, consuming more fuel than all previous maneuvers combined. This braking burn slowed Cassini enough to be captured by Saturn's gravity, transforming it from a visitor passing through into a permanent resident of the Saturnian system. The engine burn represented the most critical moment of the entire mission. If the engine failed to ignite, Cassini would fly past Saturn and continue into the outer solar system, its 7-year journey wasted. If the engine cut off early, Cassini might be captured into an orbit too eccentric for its planned mission. If the engine burned too long, the spacecraft might crash into Saturn's atmosphere before science operations could begin. Mission controllers watched helplessly as signals from the burn reached Earth over an hour after the events they described. By the time anyone knew whether the maneuver succeeded, it had been over for 70 minutes. The burn succeeded. Cassini entered orbit around Saturn, beginning a mission that would last 13 years and reveal more about the ringed planet than all previous observations in human history combined. The scientific return from Cassini justified every day of those 7 years spent in transit, every dollar of the $3.4 billion mission cost, every sleepless night spent by engineers worrying about components that could not be repaired after launch. The spacecraft discovered 7 new moons orbiting Saturn, with many more tiny moonlets found embedded within the rings. The census of Saturn's moons would continue growing as astronomers analysed Cassini's data, eventually exceeding 140 confirmed satellites. It observed seasonal changes in Saturn's atmosphere that unfolded over the 13-year orbital mission, changes invisible to flybys that passed in hours. It witnessed a massive storm in Saturn's northern hemisphere that encircled the entire planet, larger than any storm system ever observed in the solar system. Cassini studied the rings with detail that revealed them as dynamic structures rather than static features. The rings are not solid. They consist of billions of individual particles ranging from microscopic grains to house-sized chunks of nearly pure water ice. These particles collide, clump, and separate in patterns shaped by the gravity of Saturn and its moons. Tiny moons, embedded within the rings, create wakes and gaps as they orbit. Larger moons outside the rings shepherd particles into sharp edges that would otherwise spread and diffuse. The spacecraft discovered that the rings are slowly raining material down onto Saturn's atmosphere, suggesting they may be temporary features on geological timescales. Current estimates place the rings' age at perhaps 100 million years, meaning they formed long after Saturn itself and may disappear entirely within another 100 million years. The iconic rings that define Saturn in human imagination may be a fleeting phenomenon that future civilizations will huygens see. But the Huygens probe provided the mission's most dramatic moment. On December 25, 2004, Huygens separated from Cassini and began a 3-week coast toward Titan. On January 14, 2005, the probe entered Titan's atmosphere at a velocity of 13,400 miles per hour, beginning a descent that would last 2.5 hours. For the first hour, Huygens fell through stratospheric haze, its heat shield glowing orange from atmospheric friction. Parachutes deployed at 160 kilometers altitude, slowing the probe to manageable speeds while instruments analyzed the atmospheric composition. The haze that had obscured Titan for centuries revealed itself as complex organic molecules, polymers created by solar radiation, breaking apart methane in the upper atmosphere. At 60 kilometers altitude, cameras began recording images of the surface below. What they revealed was a world both utterly alien and hauntingly familiar. Dark drainage channels wound across lighter terrain, their branching patterns identical to river systems on Earth. Coastlines separated what appeared to be land from what appeared to be liquid, though the liquid was not water but methane and ethane at temperatures of -179 degrees Celsius. Huygens landed on a surface littered with rounded pebbles of water ice, smoothed by flowing liquid just as river rocks on Earth are smoothed by flowing water. The probe transmitted data for 72 minutes after landing, powered by batteries that had no hope of surviving Titan's extreme cold for more than a few hours. In those 72 minutes, humanity received more direct information about Titan's surface than all previous observations had provided about any surface beyond Mars. The images from Titan showed a world with weather and geology driven by hydrocarbons rather than water. Methane rains from the sky. Methane rivers carve canyons through water ice bedrock. Methane lakes dot the polar regions, some larger than the Great Lakes of North America. The chemistry is exotic, but the processes are familiar. Titan offered a frozen mirror of conditions that might have existed on early Earth before life emerged, a natural laboratory for studying prebiotic chemistry in an environment that has remained stable for billions of years. Cassini continued operating at Saturn until September 15, 2017, more than 13 years after entering orbit. The spacecraft had exhausted its maneuvering fuel and faced the possibility of losing attitude control. Without fuel to point its antenna toward Earth or aim its instruments at targets, Cassini would become a drifting derelict. But mission planners faced a more concerning problem than simple obsolescence. Cassini's discoveries had revealed that at least 2 of Saturn's moons might harbour conditions suitable for life. Enceladus, a tiny world barely 300 miles across, erupts with geysers of water vapour and organic molecules from a subsurface ocean. Titan's complex chemistry might support forms of life utterly unlike anything on Earth. If Cassini were allowed to drift uncontrolled, it might eventually crash into one of these moons, contaminating a potentially habitable environment with Earth microbes that had survived the journey aboard the spacecraft. Rather than risk this contamination, engineers chose to destroy Cassini in Saturn's atmosphere, where temperatures and pressures would sterilize any terrestrial hitchhikers. The grand finale mission phase sent Cassini diving through the gap between Saturn and its innermost rings 22 times, threading a space only 1,200 miles wide, at velocities exceeding 76,000 miles per hour. Each pass gathered unprecedented data about Saturn's interior structure, gravitational field, and ring composition. On September 15, 2017, Cassini made its final dive. The spacecraft transmitted data until atmospheric drag tumbled it beyond recovery, ending a mission that had spanned nearly 2 decades from launch to destruction. The signal from Cassini's final transmission took 83 minutes to reach Earth, arriving long after the spacecraft had already disintegrated in Saturn's crushing depths. From launch to final impact, the Cassini mission encompassed 20 years. The journey alone required 7 years. The orbital mission added 13 more. 2 decades of human ingenuity focused on understanding a single neighbouring world, and that world remains full of mysteries that only future missions can solve. The travel times achieved by Pioneer, Voyager, and Cassini represent what current technology makes possible for Saturn missions. 3 years, with optimal trajectories, favourable planetary alignments, and acceptance of fly-by-only encounters. 7 years for missions requiring the fuel to slow down and enter orbit. These durations are not arbitrary design choices. They emerge from fundamental physics governing how chemical rockets convert propellant into velocity, and how gravity assists can amplify that velocity by borrowing momentum from planets. The fastest journey to Saturn in history, Voyager 1's 3 years and 2 months, required a planetary alignment that occurs only a few times per century. It required trajectory optimization that sacrificed potential visits to other worlds. It required acceptance of a flyby mission that gathered data for mere days after years of travel, matching or improving on this record with a more capable spacecraft. The history of Saturn exploration demonstrates both the achievements possible with patient engineering and the constraints that patience alone cannot overcome. We have sent 4 spacecraft to the ringed planet across 4 decades of exploration. Each mission pushed the boundaries of technology available at its launch date. Each returned scientific treasures that transformed human understanding of our solar system. But that history also demonstrates how far we remain from rapid interplanetary travel. Reducing Saturn journey times from years to months would require propulsion systems that do not yet exist at practical scales. Reducing them from months to weeks would require technologies that remain theoretical. Until revolutionary propulsion becomes available, years will remain the currency in which Saturn journeys are measured. Imagine beginning the journey to Saturn on foot. You step outside your front door on a clear morning, orient yourself toward the ringed planet hanging somewhere beyond the blue sky, and start walking at a steady 3 miles per hour. This pace allows comfortable travel across Earth's surface for hours at a time. Marathon runners maintain faster speeds, but you are attempting a journey that will outlast every marathon ever run, combined by factors that dwarf comprehension. How long before you arrive at Saturn? 886 million miles, divided by 3 miles per hour, yields approximately 295 million hours of walking. Converting to years produces a journey time of roughly 33,700 years. You would walk for longer than the entire span of recorded human civilization multiplied several times over. When your journey began, woolly mammoths still roamed the steppes of Siberia. Saber-toothed cats hunted in the forests of North America. Agriculture had not been invented anywhere on Earth. Writing would not exist for another 25,000 years. The pyramids of Egypt lay more than 30 millennia in the future. The absurdity of this calculation reveals something profound about interplanetary distances. Scales that make intuitive sense for Earth-based travel become utterly meaningless when applied to the void between planets. Walking pace, the speed at which humans evolved to explore their environment, the velocity that carried our ancestors out of Africa and across every continent, cannot bridge the gaps within our own solar system in any time frame relevant to individual human lives. Walking to Saturn would require longer than modern humans have existed as a species. Consider a slightly faster option. A horse at galloping speed covers roughly 25 miles per hour, though no horse can sustain such a pace for long. Even if we imagine a magical horse capable of galloping indefinitely without rest, food, or water, the journey to Saturn would require approximately 4,000 years. The horse that began this journey would gallop through the entire Bronze Age, the Iron Age, the rise and fall of every empire in human history, arriving only in our current era. Ocean liners offer another benchmark from human transportation history. The great ships that crossed the Atlantic in the early 20th century traveled at roughly 25 to 30 miles per hour. At 30 miles per hour, the Saturn journey would require approximately 3,370 years. A passenger who boarded during the construction of Solomon's Temple would still be at sea today, having travelled continuously through the rise of Greece, the expansion of Rome, the Middle Ages, the Renaissance, and the Industrial Revolution. Perhaps you prefer driving. A car travelling at highway speeds, say 60 miles per hour, sustained continuously without stopping for fuel or rest or mechanical repair, would complete the journey in approximately 14,800,000 hours. Converting this number to more comprehensible units produces a journey time of roughly 1,685 years. Your great-great-grandchildren's great-great-grandchildren would still be generations away from arrival when the car finally crossed the distance. Consider what was happening on Earth 1,685 years ago. The Roman Empire had just split into eastern and western halves. Christianity had recently become the official religion of Rome, transforming from a persecuted sect into the dominant faith of an empire. The library at Alexandria still stood, housing knowledge that would later be lost for centuries. The journey that began in that ancient world would still be continuing when Charlemagne united Western Europe, when the Renaissance sparked in Florence, when Columbus crossed the Atlantic, when the Industrial Revolution transformed human society, when humans invented the very automobiles being imagined for this thought experiment. A car trip to Saturn would span the entire history of Western civilization, from late antiquity to the present day. Empires would rise and fall, languages would evolve beyond mutual comprehension. Technologies unimaginable at departure would become obsolete before arrival. The car itself, assuming it somehow survived the vacuum and radiation and cold of space, would become an archaeological artifact from a forgotten era by the time it reached its destination. High-speed trains represent one of the faster ground transportation options humans have developed. The Japanese Shinkansen cruises at approximately 200 miles per hour. The French TGV achieves similar velocities. At 200 miles per hour, the Saturn journey would require roughly 506 years. A passenger boarding in the early 16th century would still be travelling today. They would have departed before Shakespeare wrote his first play, before Galileo pointed his telescope at the heavens, before Newton derived the laws of motion that govern the very journey they were attempting. Commercial aircraft offer speeds that dwarf ground transportation by an order of magnitude. A Boeing 747 cruises at approximately 575 miles per hour, fast enough to cross the Atlantic Ocean in roughly 6 hours. At this velocity, the journey to Saturn would require approximately 175 years. The passengers who boarded the aircraft would be 4 generations dead before arrival. Their children would die during the journey. Their grandchildren would die. Their great-grandchildren would grow old and die. Only their great-great-grandchildren would have any chance of glimpsing Saturn's rings through the aircraft windows. 175 years ago, the American Civil War had not yet been fought. Charles Darwin had just published On the Origin of Species. The Transcontinental Railroad did not exist. Electric lighting remained decades away. Humans who lived in that world could not have imagined commercial aviation. Yet even their most advanced future transport cannot bridge interplanetary distances in individual human lifetimes. The speed of sound provides another benchmark that reveals the inadequacy of earthly velocities. At 767 miles per hour through sea-level air, sound completes the Saturn journey in approximately 131 years. A person born when the journey began would be dead for more than half a century before their shout reached the ringed planet. Sound itself, the vibrations we use for communication, for music, for warning of danger, cannot bridge interplanetary gaps in human timeframes. This means that if you scream towards Saturn right now, the sound would not arrive until roughly the year 2156. Your great-great-grandchildren might be alive to witness the arrival of a message you sent before their grandparents were born. Of course, sound cannot actually travel through the vacuum of space, but even if it could, the distances would render communication meaningless. Military aircraft push speeds considerably higher than commercial jets. The SR-71 Blackbird, the fastest air-breathing crewed aircraft ever built, achieved speeds exceeding 2,200 miles per hour during its operational career. This reconnaissance aircraft could cross the continental United States in roughly 67 minutes, outrunning surface-to-air missiles by simply accelerating until the missiles ran out of fuel. Even at this velocity, the Saturn journey would require over 45 years. A pilot beginning the flight as a young adult in their early 20s would arrive at Saturn in their late 60s, assuming they survived the journey at all. They would spend their entire adult life inside the cockpit, watching years slide past as the ringed planet gradually grew larger in the windshield. Their children would be born and raised and grown during the transit. Their career, their middle age, their retirement years would all unfold during a single unbroken flight. Bullets travel faster still, a high-powered rifle bullet exiting the muzzle at 3,000 feet per second, roughly 2,000 miles per hour depending on the specific cartridge, would complete the Saturn journey in approximately 50 years. A bullet fired today would not reach Saturn until the 2070s. The person who pulled the trigger might still be alive when the bullet arrived. If they were young and lucky and medicine continued advancing, their children would almost certainly witness the arrival, but they would be waiting longer than most human careers span, longer than most marriages last. The X-15 rocket plane achieved speeds of 4,520 miles per hour during its test program in the 1960s. This experimental vehicle pushed the boundaries of atmospheric flight, climbing to altitudes exceeding 300,000 feet, where the sky turned black and stars appeared at midday against the dark backdrop of space. Pilots earned astronaut wings for these flights despite never reaching orbit. Even at X-15 speeds, the Saturn journey would require over 22 years. 22 years represents the time from birth through college graduation. A person could earn multiple doctoral degrees in the time required to reach Saturn at X-15 velocity. They could raise children from infancy to adulthood. They could build and lose entire careers. The X-15 remains one of the fastest crewed aircraft ever built, yet it cannot deliver humans to Saturn in anything approaching convenient timeframes. The Apollo spacecraft that carried humans to the Moon travelled at approximately 25,000 miles per hour during the translunar coast phase. This velocity, achieved through the mighty Saturn V rocket, represented the fastest any human being had ever travelled at that time. At Apollo speeds, the Saturn journey would require roughly 4 years. We have finally entered territory comparable to actual interplanetary missions. 4 years would be grueling but conceivable for human crews. The psychological challenges would be immense. 4 years of confinement in a spacecraft roughly the size of a school bus. 4 years of recycled air and rationed water, and food that grew increasingly monotonous as months turned to years. 4 years of watching Earth shrink from a blue marble to a pale dot, to an invisible point lost among countless stars. But humans have survived longer periods of confinement, albeit with access to resources and variety that spacecraft cannot provide. Space shuttle missions reached orbital velocities of approximately 17,500 miles per hour. This speed represents the minimum velocity required for objects to circle Earth continuously, rather than falling back to the surface. Anything slower, and gravity wins. Anything faster, and the spacecraft begins climbing away from Earth toward higher orbits. At shuttle speed, the journey to Saturn would require just over 5.5 years. We have finally entered territory where journey times match actual missions to the outer planets. 5.5 years falls within the range achieved by real spacecraft that have actually crossed the Gulf to Saturn. But orbital velocity around Earth does not translate directly to interplanetary travel capability. A shuttle orbiting Earth at 17,500 miles per hour is not heading toward Saturn. It is circling the planet it cannot escape without additional propulsion. Escaping Earth's gravity requires additional speed beyond orbital velocity. Reaching transfer orbits that intersect Saturn's path around the Sun requires more still. The actual velocities achieved by spacecraft bound for Saturn exceed shuttle orbital speeds by significant margins, which partially explains why their journey times roughly match the calculations. New Horizons, the spacecraft that flew past Pluto in 2015 and returned the first detailed images of that distant world, holds the record for fastest launch velocity from Earth. It departed our planet at approximately 36,000 miles per hour, fast enough to pass the Moon's orbit in under 7 hours. The Apollo astronauts required 3 days to cover the same distance. New Horizons crossed it before the launch team finished their post-launch celebrations. At this velocity, sustained throughout the journey without any gravitational interference, Saturn would be reached in approximately 2.5 years. This represents a remarkable improvement over walking pace or even highway driving. 2.5 years falls within the range that individual humans could experience, could plan for, could survive with appropriate supplies and psychological support. But spacecraft do not maintain launch velocity throughout their journeys through the solar system. Gravity from the Sun slows them continuously as they climb outward through the planetary orbits. A spacecraft launched from Earth at 36,000 miles per hour does not maintain that speed. It trades velocity for distance, slowing as it climbs the gravitational hill out of the Sun's influence. By the time it reaches the outer solar system, it has lost significant speed to this gravitational braking. New Horizons actually used a Jupiter gravity assist to reach Pluto in 9.5 years, rather than the much longer time a direct trajectory would have required. And even with that assist, the spacecraft merely flew past Pluto rather than entering orbit. Slowing down to orbit would have required fuel that the spacecraft did not carry, adding years to the journey time or requiring a massive increase in launch vehicle size. The Parker Solar Probe has achieved the highest speeds of any human-made object in history, reaching approximately 430,000 miles per hour during its closest approaches to the Sun. At this velocity, the journey to Saturn would require only 85 days, less than 3 months. Spring would turn to summer before the journey ended. You could leave Earth in January and arrive at Saturn before April. But the Parker Solar Probe achieves these spectacular speeds, specifically because it falls deep into the Sun's gravity well. Like a ball rolling down a steep hill, the probe gains velocity as it plunges toward the Sun's surface, reaching its maximum speed at closest approach before climbing back out and slowing down. The Sun's gravity provides the acceleration. A spacecraft heading outward towards Saturn cannot benefit from this effect because it travels away from the Sun rather than toward it. Spacecraft traveling to the outer solar system fight against the Sun's gravitational pull the entire journey. They burn fuel to gain velocity, then watch helplessly as solar gravity bleeds that hard-won speed away mile by mile. The farther they travel from the Sun, the weaker the gravitational braking becomes. But they never escape it entirely. Even at Saturn's distance, the Sun's gravity determines orbital dynamics, pulling at everything that passes through its domain. The energy requirements for reaching Saturn reveal why journey times remain so stubbornly long despite decades of engineering advancement. Accelerating a spacecraft to interplanetary velocities demands enormous quantities of energy. Every additional mile per hour requires fuel that adds mass that requires more fuel to accelerate. The exponential nature of this relationship means that cutting journey times in half requires far more than doubling the fuel supply. Consider the energy contained in a typical spacecraft heading towards Saturn. A probe weighing 5,000 kilograms and traveling at 6 kilometers per second relative to its destination carries kinetic energy equivalent to roughly 20 tons of TNT. This energy must come from somewhere. Chemical rockets extract it from the molecular bonds of their propellants. But regardless of source, the energy must be provided, carried from Earth, and converted into velocity through some propulsion mechanism. To understand these energy scales in more familiar terms, consider that the kinetic energy of a spacecraft arriving at Saturn exceeds the total energy consumption of a small city for an entire year. A single mission to the outer planets burns more energy than most humans will use in their entire lifetimes. The launch alone consumes enough fuel to power thousands of automobiles for thousands of miles each. Stopping at the destination requires dissipating this kinetic energy. The spacecraft cannot simply slam into Saturn's atmosphere at orbital velocities without being destroyed. It must slow down, which means either burning fuel to decelerate or using atmospheric drag in a controlled manner. Each option has costs and limitations that constrain mission design. The fundamental limit on chemical rocket performance comes from the energy density of propellants. When hydrogen and oxygen combine, they release energy by forming water molecules. This reaction has powered every crewed space mission in history, and most robotic missions as well. But the energy released by chemical bonds represents only a tiny fraction of the energy locked within atomic nuclei. Nuclear fission releases roughly 2 million times more energy per unit mass than chemical combustion. If we could harness these energy sources for propulsion, journey times to Saturn could shrink dramatically. The same spacecraft could reach Mars in a matter of days rather than months, but converting nuclear energy into thrust remains challenging. Nuclear thermal rockets, which heat hydrogen propellant by passing it through a fission reactor, were successfully tested during the 1960s. The NERVA program demonstrated that such engines could operate reliably and produce thrust levels suitable for crewed missions, yet political opposition, budget constraints, and shifting priorities killed the program before any nuclear rocket flew an operational mission. Ion engines offer a different approach to high-efficiency propulsion. These devices accelerate ionized gas using electric fields, achieving exhaust velocities 10 times higher than chemical rockets. The higher exhaust velocity means more velocity change per unit of propellant consumed. Spacecraft using ion engines can carry less fuel while achieving greater speeds. But ion engines produce thrust measured in millinewtons, roughly the force of a sheet of paper resting on your palm. They accelerate spacecraft gradually over months and years, rather than rapidly over minutes. An ion-propelled mission to Saturn would be efficient but not fast. The journey might require less fuel than a chemical rocket would need, but the travel time would remain measured in years. The speed of light provides the ultimate benchmark against which all other velocities must be compared. At 670 million miles per hour, light completes the journey to Saturn in approximately 67 minutes during closest approach and 90 minutes at maximum separation. This represents the absolute fastest that any information or physical object could theoretically travel according to our current understanding of physics. Nothing with mass can reach light speed. As objects accelerate toward this cosmic limit, their effective mass increases, requiring more and more energy for each additional increment of velocity. The energy required to accelerate a spacecraft to light speed is literally infinite. The laws of physics, as we understand them, forbid any massive object from reaching or exceeding this barrier. But even approaching significant fractions of light speed remains far beyond any propulsion technology currently imagined or under development. The energy requirements scale with the square of velocity, meaning that reaching 10% of light speed requires 100 times the energy of reaching 1% of light speed. The mathematics rapidly becomes prohibitive. Reaching just 1% of light speed, roughly 6.7 million miles per hour, would allow Saturn journeys measured in days rather than years. The ringed planet would be accessible in roughly 5 to 6 days, comparable to an ocean crossing by ship rather than transcontinental flight. Still, 6 days compares favorably to 6 years. But accelerating a modest spacecraft to this velocity would require energy equivalent to global civilization's total energy production over significant time periods. Consider what 1% of light speed means in practical terms. A spacecraft traveling at this velocity would cross the distance from New York to Los Angeles in approximately 1/3 of a second. It would reach the Moon in roughly 2 minutes. It would pass Mars at closest approach in under 4 minutes. These journey times sound like science fiction, because they are. No propulsion technology on any realistic development timeline could achieve such velocities. Antimatter propulsion offers the theoretical maximum energy density possible according to known physics. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy, according to Einstein's famous equation. This represents perfect efficiency, extracting every possible joule from the matter consumed. By comparison, nuclear fission converts less than 1% of fuel mass into energy. Chemical combustion converts a percentage so small it rounds to 0 on nuclear scales. The atoms in your gasoline remain atoms after combustion, slightly rearranged but fundamentally intact. Antimatter annihilation destroys the atoms entirely, releasing energy that dwarfs chemical reactions by factors of billions. A spacecraft powered by matter-antimatter annihilation could theoretically reach Saturn in days rather than years. The energy density would allow continuous acceleration and deceleration at comfortable levels, covering interplanetary distances in timeframes that match human attention spans rather than human lifespans. But producing antimatter requires more energy than the antimatter contains. This is not an engineering limitation awaiting clever solutions. It follows directly from the laws of thermodynamics. Creating matter-antimatter pairs from energy is inherently less efficient than the reverse process, because some energy always escapes as radiation rather than being captured in particle masses. Current particle accelerators generate only nanograms of antimatter annually, quantities so small they would be invisible to the naked eye. The cost of this production exceeds trillions of dollars per gram when calculated from facility construction and operating expenses. The total amount of antimatter ever produced by humanity would not power a small flashlight for more than a few minutes. The spectrum of speed from walking pace to light speed spans a factor of over 200 million. At one end stands the 3 miles per hour that humans evolved to sustain while foraging across African landscapes. At the other end stands 670 million miles per hour, the cosmic speed limit imposed by the structure of space-time itself. Everything humanity has ever built for transportation falls somewhere along this spectrum, clustered heavily toward the slow end where our intuitions developed. Commercial aircraft operate at roughly 1/1,000,000th of light speed. The fastest spacecraft humanity has ever launched achieved approximately 1/50,000th of light speed during its closest solar approach. The vast majority of the velocity spectrum remains inaccessible to any technology we can currently build or seriously propose building within foreseeable timeframes. Journey times to Saturn depend entirely on where along this spectrum we can practically travel. Current technology places us in the range of tens of thousands of miles per hour, yielding journeys measured in years. Advanced nuclear propulsion might push us into hundreds of thousands of miles per hour, potentially reducing journey times to months for flyby missions. Revolutionary technology that does not yet exist might approach millions of miles per hour, bringing Saturn within reach of expeditions lasting weeks. But each step up the velocity ladder requires exponential increases in energy availability and propulsion efficiency. The gap between what we can build today and what physics theoretically allows spans orders of magnitude that no foreseeable engineering breakthrough will bridge. We do not lack imagination for faster travel. Engineers and physicists have proposed propulsion concepts that would revolutionize space travel if they could be built. What we lack are the materials, the energy sources, and the engineering solutions that would transform imagination into hardware capable of surviving launch, operating reliably across years or decades, and delivering payloads to destinations separated from Earth by hundreds of millions of miles. The dream of rapid interplanetary travel, of Saturn being as accessible as Australia is today, requires physics and engineering that remain firmly in the future. For now, and for the foreseeable decades ahead, Saturn journeys will continue to be measured in years. The distance demands patience that matches its scale. Human ambition must accommodate cosmic reality, and cosmic reality remains stubbornly indifferent to our preference for speed. Ion propulsion already works. This statement requires emphasis because so many discussions of advanced space travel focus on theoretical concepts that may never leave laboratory benches. Ion engines have flown. They have completed missions. They have propelled spacecraft to asteroids, comets, and dwarf planets across the solar system. The technology has matured from laboratory curiosity to proven flight hardware over 3 decades of incremental development and operational experience. An ion engine operates on principles fundamentally different from chemical rockets. Instead of burning propellant to create hot expanding gases, an ion engine ionizes a propellant, typically xenon gas, by stripping electrons from its atoms. The resulting positively charged ions are then accelerated through powerful electric fields, shooting out the back of the engine at velocities far exceeding anything chemical combustion can achieve. The exhaust velocity of a typical ion engine exceeds 30 kilometers per second, nearly 10 times higher than the best chemical rockets burning hydrogen and oxygen. This efficiency advantage translates directly into fuel savings through the mathematics of the rocket equation. Ion-propelled spacecraft can achieve equivalent velocity changes with roughly 1/10 the propellant mass that chemical alternatives would require. Less fuel means smaller spacecraft, cheaper launches, or more ambitious mission profiles. The Dawn spacecraft demonstrated ion propulsion's potential for deep space exploration in spectacular fashion. Launched in 2007, Dawn carried 3 xenon ion engines that would operate for a cumulative total exceeding 50,000 hours during the mission. The spacecraft visited the asteroid Vesta in 2011, spending 14 months orbiting and studying this protoplanetary remnant. Then Dawn did something no spacecraft had ever done before. It left Vesta orbit and travelled to a completely different destination. In 2015, Dawn entered orbit around the dwarf planet Ceres, becoming the first spacecraft to orbit 2 different solar system bodies beyond Earth and Moon. Chemical rockets could never have enabled this mission profile. The fuel required to leave Vesta orbit and travel to Ceres would have exceeded any practical spacecraft's capacity. Ion propulsion made the impossible merely difficult, allowing a single spacecraft to accomplish what would otherwise have required 2 separate missions. But ion engines generate thrust measured in millinewtons. To understand what this means practically, hold a single sheet of paper flat on your palm. The weight you feel, that gentle pressure of a few grams against your skin, roughly equals the thrust of an ion engine. This minuscule force cannot lift anything against Earth's gravity. It cannot provide the dramatic acceleration that chemical rockets deliver during launch. What it can do is push continuously for months and years, gradually accumulating velocity that eventually exceeds what brief chemical burns could achieve. Ion propulsion excels at patience, fails completely at urgency. A spacecraft using ion engines must accept leisurely acceleration profiles that span years rather than minutes. The Dawn mission required nearly 4 years to travel from Earth to Vesta, despite using one of the most efficient propulsion systems ever flown. Ion engines are marathoners, not sprinters. A Saturn mission using ion propulsion would require 3 to 5 years depending on available electrical power and launch window timing. This represents no improvement over chemical rockets using gravity assists. The efficiency advantage of ion engines, their ability to extract more velocity from less propellant, is completely offset by their glacial acceleration profile. For Saturn missions where journey time matters, ion propulsion offers fuel savings but not time savings. More powerful electric propulsion systems are under development that might change this equation. Variable specific. Impulse magnetoplasma. Rockets, known by the acronym VASIM-R, the promised thrust levels hundreds of times higher than current ion engines, while maintaining the high exhaust velocities that make electric propulsion efficient. A VASIM-R engine operating at full power could accelerate spacecraft fast enough to reach Saturn in just over a year under optimal conditions. The physics behind VASIM-R involves heating plasma to temperatures exceeding 1 million degrees using radio frequency energy, then channeling that superheated gas through magnetic nozzles that direct its expansion into thrust. The engine can adjust its operating parameters in flight, trading between high thrust at lower efficiency and lower thrust at higher efficiency depending on mission phase requirements. But power remains the critical constraint that limits all electric propulsion concepts. VASIM-R engines require megawatts of electrical power to achieve their promised performance. Generating megawatts in space requires either enormous solar arrays or nuclear reactors, and both options carry substantial penalties. Solar arrays become progressively less effective as spacecraft travel farther from the Sun. The intensity of sunlight diminishes with the square of distance. At Saturn's orbit, roughly 9.5 times farther from the Sun than Earth, solar intensity drops to approximately 1% of Earth orbit levels. A solar array that generates 100 kilowatts at Earth would produce barely 1 kilowatt at Saturn. Powering a megawatt-class engine would require solar arrays measured in football fields, arrays so massive that no existing rocket could launch them. Nuclear reactors could provide consistent power regardless of solar distance, but they add mass, cost, and political complications to any mission. Space-rated nuclear reactors require extensive shielding to protect sensitive electronics from radiation. They require reliability guarantees spanning decades because no repair crew can service a reactor millions of miles from Earth. And they require political approval that has historically proven difficult to obtain for any space mission carrying nuclear materials. Nuclear thermal propulsion offers a more direct approach to faster Saturn journeys that sidesteps the power generation problem entirely. This technology heats hydrogen propellant by passing it through a nuclear fission reactor, then expels the superheated gas through a conventional rocket nozzle. The nuclear reaction provides heat, not electricity. The propellant provides thrust through expansion, just like a chemical rocket. The crucial advantage of nuclear thermal rockets comes from temperature. Chemical rockets are limited by the temperatures their combustion chambers can withstand. The materials that contain the reaction set an upper limit on how hot the exhaust gases can become. Nuclear reactors can achieve much higher temperatures because the heat source is nuclear rather than chemical, and reactor cores can be designed to survive conditions that would melt any combustion chamber. Higher temperatures mean faster exhaust velocities. Nuclear thermal rockets achieve exhaust velocities roughly twice those of the best chemical rockets, approximately 9 kilometers per second compared to 4.5. This doubling of efficiency translates directly into shorter journey times or larger payloads for equivalent missions. The United States developed and tested nuclear thermal rockets during the 1960s under a program called NERVA, the Nuclear Engine for Rocket Vehicle Application. Engineers at Los Alamos National Laboratory designed and built reactors specifically optimized for rocket propulsion. Test stands in the Nevada desert fired these engines repeatedly, demonstrating that nuclear thermal propulsion worked exactly as theory predicted. The NERVA program achieved remarkable success before its cancellation. Engines operated for over an hour at full power, demonstrating restart capability that chemical upper stages of that era could not match. Performance exceeded design specifications. Reliability met the standards required for crewed missions. A flight-ready nuclear rocket could have been built within a few years if funding had continued. But priorities shifted after the Apollo program wound down and ambitious Mars mission plans were abandoned. The Nixon administration slashed NASA's budget and cancelled programs that no longer served immediate political goals. NERVA died not because the technology failed, but because the nation lost interest in the destinations the technology could reach. Recent decades have seen renewed interest in nuclear thermal propulsion. NASA's current plans for human Mars missions assume nuclear thermal engines for the interplanetary transit phase. The agency has funded development programs aimed at demonstrating flight-ready nuclear propulsion within the 2030s. If these programs succeed, the same technology could eventually enable faster Saturn missions. Applied to Saturn, nuclear thermal propulsion could theoretically reduce journey times by 40 to 50% compared to chemical rockets using gravity assists. A nuclear thermal mission might reach Saturn in 18 to 24 months, rather than the 3 to 7 years that chemical missions have required. This still represents a substantial journey measured in years rather than months, but it begins approaching timeframes that human crews might tolerate with appropriate supplies and psychological support. Nuclear pulse propulsion represents a far more extreme application of nuclear energy to space travel, one that remains technically feasible but politically impossible. Project Orion, studied extensively during the late 1950s and early 1960s, proposed propelling spacecraft using controlled nuclear explosions. The concept sounds insane until you examine the engineering details, at which point it sounds merely audacious. The Orion spacecraft would carry thousands of small nuclear devices in its hold. A mechanism would eject these bombs one at a time out the back of the spacecraft, detonating them at precise distances behind a massive pusher plate. The explosion's plasma would slam into the pusher plate, transferring momentum through a shock absorption system that converted the violent impulse into smooth acceleration. The theoretical performance of nuclear pulse propulsion staggered the engineers who studied it. Unlike conventional rockets that must carry all their propellant as dead weight until burned, Orion's bombs provided both fuel and oxidizer in compact packages. The energy density of nuclear explosions so far exceeded chemical reactions that performance scaled with spacecraft size in counterintuitive ways. Larger Orion spacecraft actually became more efficient because the ratio of bomb yield to structural mass improved. An Orion spacecraft could have reached Mars in 4 weeks, rather than the 9 months that chemical rockets require. Saturn might have been accessible in 3 to 4 months, compared to years with conventional propulsion. The specific impulse, a measure of propulsion efficiency, exceeded anything else imaginable with 1960s technology by factors of 10 or more. Freeman Dyson, the legendary physicist who worked on the project, later wrote that Orion represented the first technology capable of making interstellar travel conceivable. The same propulsion system that could reach Saturn in months could potentially reach nearby stars in decades or centuries rather than millennia, but nuclear pulse propulsion died, along with atmospheric nuclear testing. The Partial Test Ban Treaty of 1963 prohibited nuclear explosions in space, effectively ending Orion development regardless of its technical merit. The treaty exists for excellent reasons, having nothing to do with space travel, reasons involving radioactive fallout and arms race dynamics that justifiably concerned Cold War leaders. Whether nuclear pulse propulsion could ever be politically acceptable, regardless of technical capability, remains deeply questionable. Some researchers have proposed variants using pure fusion devices that produce minimal radioactive fallout, or even antimatter catalyzed reactions that might sidestep treaty limitations. But these concepts remain theoretical, and the political barriers seem at least as formidable as the technical ones. Humanity is unlikely to launch thousands of nuclear weapons into space, regardless of the propulsion benefits, unless circumstances change dramatically. Fusion propulsion offers perhaps the most promising path to rapid interplanetary travel without the political baggage of nuclear explosions. Fusion reactions, the same processes that power the Sun, release energy by combining light atomic nuclei into heavier ones. When hydrogen nuclei fuse into helium, they release energy equivalent to about 0.7% of the original mass. This sounds small until you remember that chemical reactions convert essentially 0% of mass into energy on any meaningful scale. The energy yield per unit mass from fusion exceeds chemical reactions by millions of times and exceeds fission by factors of 4 to 5. A fusion-propelled spacecraft could theoretically achieve exhaust velocities measured in thousands of kilometers per second, compared to the single-digit kilometers per second available from chemical rockets. This performance advantage would transform interplanetary travel from expeditions lasting years into voyages lasting weeks. A spacecraft accelerating at just 1/10 of Earth's gravity using fusion propulsion could reach Saturn in approximately 1 month, decelerating to arrive at orbital velocities rather than screaming past in a brief flyby. Such a vehicle could carry enough fuel for round trips rather than one-way journeys. It could respond to discoveries by changing course rather than following predetermined trajectories planned years in advance. Fusion propulsion would make the outer solar system accessible in the same way that jet aircraft made intercontinental travel accessible. But practical fusion propulsion remains decades away, if it proves achievable at all. Sustained fusion reactions require temperatures exceeding 100 million degrees Celsius, hot enough that no material container can survive direct contact with the reacting plasma. Magnetic fields must confine the reaction, holding superheated matter away from walls that would instantly vaporize on contact. Major research programs have pursued controlled fusion for over 70 years. The ITER experimental reactor under construction in France represents humanity's most ambitious attempt to demonstrate net energy production from fusion. Even if ITER succeeds beyond its designer's hopes, decades more work would be required to miniaturize fusion systems for spacecraft applications. The reactors that might someday power electric grids would be far too massive and delicate for space travel, without revolutionary advances in materials and design. Fusion propulsion for spacecraft lies even farther in the future than fusion power for electricity. The engineering challenges of creating a compact, reliable fusion engine that can operate for months in the space environment, surviving launch vibrations, radiation exposure, and temperature extremes, exceed anything currently foreseeable. When fusion spacecraft might actually fly remains a question measured in decades at minimum, perhaps centuries, perhaps never. Antimatter propulsion represents the theoretical maximum energy density possible according to known physics. When matter and antimatter meet, they annihilate completely, converting their entire combined mass into energy, according to Einstein's famous equation. This represents 100% efficiency, extracting every possible joule from the matter consumed. By comparison, fusion converts roughly 0.7% of mass into energy. Fission converts less than 0.1%. Chemical combustion converts a percentage so small it rounds to zero on nuclear scales. Antimatter stands alone as the ultimate fuel, containing more energy per gram than any other known substance. A gram of antimatter, annihilated with a gram of ordinary matter, releases energy equivalent to roughly 43 kilotons of TNT, nearly 3 times the yield of the Hiroshima bomb. An antimatter rocket producing just milligrams of propellant annihilation could theoretically reach Saturn in days rather than years. The specific impulse would exceed any other propulsion concept by orders of magnitude, but producing antimatter requires more energy than its annihilation releases. This is not an engineering limitation awaiting clever solutions. It follows directly from the laws of thermodynamics. Creating matter-antimatter pairs from energy is inherently less efficient than the reverse process because some energy always escapes as radiation, rather than being captured in particle masses. Current particle accelerators generate only nanograms of antimatter annually, quantities so small they would be invisible to the naked eye. The cost of this production exceeds trillions of dollars per gram when calculated from facility construction and operating expenses. The total amount of antimatter ever produced by humanity would not power a small flashlight for more than a few minutes. No storage technology can contain antimatter in useful quantities. Antimatter annihilates instantly on contact with any normal matter, including the walls of any container. Magnetic traps can suspend charged antimatter particles in vacuum, but only in quantities, measured in individual atoms or small clusters. Scaling up to the milligrams or grams needed for propulsion remains so far beyond current capability that no serious development timeline exists. Antimatter propulsion is less a technology under development than a theoretical ceiling against which all other concepts are measured. It represents what might be possible if physics we do not yet understand could be harnessed in ways we cannot yet imagine. For practical mission planning purposes, antimatter propulsion does not exist. Solar sails offer a propulsion method requiring no propellant at all, sidestepping the rocket equation entirely. Large reflective sheets capture momentum from sunlight, gradually accelerating spacecraft away from the sun. The photons that strike the sail impart tiny impulses with each collision. Reflected photons transfer twice their momentum compared to absorbed photons, making reflective sails more efficient than absorbing surfaces. The acceleration produced by solar sails is minuscule, measured in fractions of a millimeter per second squared. A solar sail spacecraft accelerates roughly 100,000 times more slowly than a falling object on Earth. But this acceleration continues indefinitely, without consuming any fuel. Over months and years, the accumulated velocity can exceed what chemical rockets achieve in brief burns. For journeys to Saturn, solar sails face a fundamental challenge inherent to their operating principle. The same inverse square law that dims sunlight at greater distances also reduces the thrust available to solar sails. A sail experiencing 1 unit of acceleration at Earth's orbit feels only 1/81st of that acceleration at Saturn's distance. The sail becomes progressively less effective exactly when sustained thrust would be most valuable. Laser push sails could overcome this limitation by providing thrust from powerful ground-based or space-based lasers rather than from sunlight. A beam of coherent light maintains its intensity over vast distances, far better than diverging sunlight. A sufficiently powerful laser could push a sail all the way to Saturn at constant or even increasing thrust levels. The Breakthrough Starshot project, funded by Russian billionaire Yuri Milner, proposes using laser-pushed sails to send gram-scale probes to Alpha Centauri at 20% of light speed. The concept involves gigawatt-class laser arrays, pushing ultra-thin sails carrying only the most minimal instrumentation. At 20% of light speed, the probes would reach our nearest stellar neighbour in roughly 20 years, returning images and data from another star system within a human lifetime. Scaled-up versions of this technology might someday enable rapid interplanetary travel as well. A laser capable of pushing gram-scale probes to interstellar velocities could certainly accelerate heavier spacecraft to interplanetary velocities. Saturn might become accessible in weeks rather than years if sufficiently powerful laser arrays could be constructed. But laser propulsion faces enormous engineering challenges that current technology cannot address. Construction of gigawatt-class lasers operating continuously would require power infrastructure that does not exist. Development of sails that can survive the intense heating such beams would produce requires materials science breakthroughs that have not occurred. Political and safety challenges of pointing powerful lasers into space from Earth's surface raise concerns that no technical solution can fully address. Perhaps the most important question is not how fast we could reach Saturn, but why we would want to badly enough to justify the enormous investments faster travel would require. Speed costs money. Every technology capable of reducing Saturn journey times from years to months requires development programs measured in billions of dollars and decades of effort. What makes Saturn worth this investment? The answer lies not with Saturn itself, though the giant planet harbours mysteries that scientists yearn to solve. The answer lies with Saturn's moons, two of which have emerged as among the most compelling targets for astrobiology in the entire solar system. Titan, Saturn's largest moon and the second largest moon in the solar system, possesses the only dense atmosphere besides Earth's anywhere among the planets and moons we have explored. This thick orange haze, composed primarily of nitrogen with methane and complex hydrocarbons, creates surface pressure roughly 50% higher than Earth's sea-level atmosphere. A human standing on Titan without a spacesuit would be crushed and frozen, but they would not suffocate from lack of pressure. Lakes of liquid methane and ethane dot Titan's polar regions, some larger than the Great Lakes of North America. Rivers of hydrocarbons carve channels through water ice bedrock. Rain falls from orange clouds onto landscapes that would look hauntingly familiar if not for the alien chemistry that shapes them. Titan has weather, seasons, and geology driven by hydrocarbons rather than water, creating a world unlike anywhere else we have directly observed. Complex organic chemistry occurs continuously in Titan's atmosphere, producing compounds that might resemble the prebiotic chemistry from which life emerged on Earth 4 billion years ago. Solar radiation breaks apart methane molecules in the upper atmosphere. The resulting fragments recombine into increasingly complex organic polymers that rain down onto the surface, accumulating in deposits that might contain clues about how chemistry becomes biology. The chemistry occurring on Titan represents a natural experiment running for billions of years. If the same processes that led to life on Earth occur readily wherever conditions permit, Titan's organic deposits might contain molecular signatures pointing toward biology. If life requires conditions specific to Earth, Titan's chemistry might reveal where those requirements break down, helping scientists understand what makes our planet uniquely hospitable. A mission capable of extensive Titan exploration could reveal whether life's building blocks form readily under conditions very different from those that produced life on our planet. If organic complexity arises easily from simple starting materials and energy input, life might be common throughout the cosmos. If Titan's chemistry reaches dead ends that prevent the emergence of self-replicating systems, we might better understand what makes Earth special. Enceladus, a tiny moon barely 300 miles in diameter, has emerged as perhaps the most exciting astrobiology target in the solar system despite its diminutive size. This ice-covered world erupts with geysers of water vapor and ice particles from cracks near its south pole. Jets that spray material into space, where spacecraft can sample it directly. The geysers originate from a subsurface ocean of liquid water, kept fluid by tidal heating from Saturn's gravity. As Enceladus orbits the giant planet, Saturn's gravity flexes the moon's interior, generating heat through friction. This heat maintains liquid water beneath the icy crust, creating an environment that might be habitable for microbial life. Cassini flew through Enceladus's plumes multiple times, analyzing the composition of material erupting from the subsurface ocean. The spacecraft detected organic molecules, hydrogen gas suggesting active hydrothermal chemistry, and salts indicating water-rock interactions. The subsurface ocean appears to possess the chemical ingredients and energy sources that life requires on Earth. On Earth, hydrothermal vents on the ocean floor support thriving ecosystems completely independent of sunlight. Bacteria derive energy from chemical reactions between hot water and rock. Larger organisms feed on these bacteria. Entire food webs exist in perpetual darkness, sustained only by the energy flowing from Earth's interior. If similar conditions exist in Enceladus's ocean, similar ecosystems might have evolved there. Ocean worlds like Enceladus represent a new category of potentially habitable environment that astronomers barely imagined a generation ago. Life on Earth requires liquid water, energy sources, and chemical building blocks. Enceladus appears to possess all three, packaged beneath an icy crust that protects the ocean from radiation and provides stability over geological timescales. A mission capable of landing on Enceladus and sampling its ocean material could potentially detect biosignatures, chemical patterns that indicate biological activity. Such a discovery would transform human understanding of life's place in the cosmos. Finding even microbial life on another world would prove that biology emerges readily when conditions permit, suggesting that life might be common throughout the universe. The implications for philosophy, religion, and humanity's sense of cosmic significance would be profound beyond calculation. Saturn's rings themselves present scientific mysteries that closer examination could resolve. Recent data revealed that the rings are surprisingly young, perhaps only 100 million years old despite Saturn's 4.5 billion year history. The rings appear to be slowly raining material onto Saturn's atmosphere, suggesting they may disappear entirely within another 100 million years. The youth of the rings raises profound questions about their origin. If Saturn has existed for 4.5 billion years, but its rings formed only 100 million years ago, what created them? The leading hypothesis suggests a moon wandered too close to Saturn and was torn apart by tidal forces. The debris from this destroyed moon gradually spread into the ring system we observe today. But confirming this hypothesis requires detailed study of ring composition and structure that only close observation can provide. Understanding how the rings formed, why they persist, and how they interact with Saturn's numerous small moons could reveal processes relevant to planetary formation throughout the cosmos. Ring systems may have been common in our solar system's past, playing roles in moon formation that we do not yet understand. Saturn's rings offer the best laboratory for studying these dynamics. The hexagonal storm at Saturn's North Pole presents another mystery that defies easy explanation. This geometric weather pattern, larger than Earth itself, has persisted for decades without dissipating. The six-sided shape rotates with the planet, maintaining its structure despite the chaotic nature of atmospheric dynamics. No other planet exhibits a similar feature. Earth storms are circular because the physics of rotating fluids naturally produces circular patterns. How Saturn's atmosphere maintains a hexagonal structure remains unclear. The rapid rotation of Saturn's cloud tops, completing a full turn every 10.5 hours, creates wind patterns unlike anything on slower rotating planets. Understanding the hexagonal storm could reveal fundamental principles about atmospheric dynamics applicable to worlds throughout the cosmos. human missions to Saturn remain beyond current planning horizons. The journey times achievable with existing technology, 3 to 7 years one way, create supply requirements and psychological challenges that no crewed mission design has seriously addressed. Astronauts would need to carry years of food, water, and oxygen. They would need to maintain sanity through years of confinement in cramped spacecraft. They would need to remain healthy despite years of exposure to cosmic radiation and zero gravity. Reducing those journey times from years to months would transform Saturn from a distant observation target into a potential destination for human explorers. Technologies capable of enabling such journeys do not yet exist in practical form, but the scientific rewards waiting at Saturn justify continued investment in propulsion research that might someday make the ringed planet accessible to human presence. The distance to Saturn represents both a challenge and an opportunity. 886 million miles of void separate us from one of the solar system's most fascinating destinations. Every technology we develop to bridge that void faster would have applications throughout the solar system and potentially beyond. Propulsion systems capable of reaching Saturn in months could reach Mars in weeks and the outer planets in reasonable timeframes. The journey to Saturn, whatever its duration, represents humanity reaching outward toward worlds that ancient astronomers observed as wandering points of light. They named this slow-moving world after the Roman god of agriculture, never imagining that telescopes would reveal rings and moons and mysteries that continue surprising us millennia later. How long would it really take us to reach Saturn? The answer depends entirely on choices we have not yet made and technologies we have not yet developed. With current chemical rockets and gravity assists, 3 to 7 years depending on mission requirements. With nuclear thermal propulsion that could be developed within decades, perhaps 18 months. With fusion or antimatter propulsion that may never prove practical, the ringed planet waits in the outer darkness, surrounded by moons that might harbour oceans and atmospheres that might harbour chemistry, that might harbour life. The journey there remains long by any human standard, but every year brings new technologies that might shorten the path, new discoveries that might justify the effort, and new dreamers who imagine crossing the void that separates us from worlds we can see but have only begun to explore. Saturn is not impossibly far. It merely lies beyond the reach of impatience. With sufficient time, sufficient energy, and sufficient will, any distance within our solar system becomes accessible to the species that built spacecraft from dreams and mathematics. The question is not whether humanity can reach Saturn. We have reached it 4 times already, sending robotic emissaries that transformed our understanding of this magnificent world. The question is how long we are willing to wait for each journey to complete, and whether we will develop the technologies that might someday allow humans to stand beneath those impossible rings and look back toward the distant blue dot they called home.